Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tear. I haven't made a video on this channel for probably over a month. I apologize for that. I mean, I don't know if you guys know, but I met a woman about a month ago. I have a new girlfriend now. I've been spending a lot of time with her. That's one thing that's going on. Also, I'm kind of worried about what's going on with Trump and everything. But I decided I'm gonna start a new feature on this channel, and I'm gonna do this every day, at least for now. I have a book that I wrote. Or actually, it's a series of three books. It's a three volume series called the Math Lovers Book, which I wrote from 2019 to 2022. And you guys can buy this if you want. It's available on Amazon, Amazon.com. You can type the Math Lovers Book, and there's three volumes. Volumes one, volume two, and also volume three is called Problems and Solutions. And I think I should give you a little bit of an overview. So, volume one is kind of recreational math. Both of these, so volumes one and two are really sort of like math texts, but volume one is more recreational math, and volume two is more academic. And this is all kind of advanced high school or maybe undergraduate level math. It's not really that advanced. And I think it's fun. If you guys like math, which I think most of you guys do who are following me on this channel, I think you'll really enjoy this book or this whole series. And volume three is problems and solutions. So this has problems pertaining to all the parts of volumes one and two. There's exercises, and there's also solutions to all the odd number problems. I don't give solutions to the even number problems. I like to have you do those yourself. So anyway, that's kind of an overview of all three of these volumes. And volume one, that's what I'm going to start with. Like I said, this is the more recreational math. And in case you're interested, this picture here is a picture of what's called a Penrose tiling. It's a pretty amazing mathematical construction. It was discovered by a very famous mathematician and physicist named Roger Penrose. I believe he came up with this tiling in 1974. And the thing that's really fascinating about it is it's an aperiodic tiling. It's what's called a quasi-periodic tiling. It never quite repeats itself, but it gets arbitrarily close, and also has fivefold symmetry. But I'm kind of digressing here. Let me go into the book. So first, I'm going to give you a little bit over a book of view of volume one. This is the table of contents. I don't know if you can read all this. I'll just tell you what's in the book. There's 10 chapters. There's three parts, and there's a total of 10 chapters. So part one is on numbers, and that has four chapters. Chapter one is numbers and number systems. And chapter two is on rational numbers, in other words, fractions. Chapter three is on real numbers. That includes irrational numbers as well as rational numbers like square roots and pi and e. And then chapter four is on complex numbers. Those are numbers of the form a plus bi, where I is what's called the imaginary constant or the imaginary unit. And then that's chapter one. That's on numbers. Chapter two is on abstract algebra. So this concerns things that are a little more abstract than just numbers. I start with sets. Chapter five is on sets. Chapter six is on what are called groups. I don't know how many of you guys know what a group is, but group theory is a very important area of math that was first invented in the 19th century as a way to describe symmetry. So whenever you work with symmetry, the mathematical theory of symmetry is called group theory. So there's some kind of basic group theory in chapter six. Chapter seven's on logic. Logic is kind of how math is built. I mean, all math involves logic, just kind of being able to prove things. You have to prove things in math, and logic is the whole theory of how to do proofs. And then chapter 8 is a very important application of logic. That's computation, the theory of computation. That's how computers work. And all computers use logic. That's how they work. So that's section 2 on abstract algebra. Finally, section 3 is on chaos and fractals. This is a pretty new area of math. I think it was really just developed in the latter half of the 20th century, and it's still a pretty active field. So in chapter 9, I talk about dynamical systems, and dynamical systems are where you see chaos come in. Whenever you have kind of nonlinear dynamical systems, they exhibit what's called chaos. And chapter 10 is a very important application of chaos, namely fractals. It turns out that chaotic phenomena aren't as chaotic as you might think. They actually have some structure to it, and that structure is known as fractals. These are sets with dimensions that don't have to be integers. They're kind of neat sets, but we'll get into all that. That's what's in this volume 1, and like I said, they're kind of fun topics, I think. So anyway, today I'm going to start section 1.1. It's a very short section. So this is the first section in the book. It's called Numbers and Number Systems. Yeah, well, that's the name of the chapter, actually. So I'm going to talk about, this is just what are numbers. So this is the whole section right here, this one page. And on the right, I have a Venn diagram. So these are different types of numbers. And probably the first numbers you ever learn are what are called natural numbers or counting numbers or whole numbers. No, natural numbers. And there's different definitions of natural numbers. Some people, I think traditionally people like to start counting with 1. I mean, 0 wasn't even discovered, at least in the Western world, until Fibonacci was the first person to introduce 0 to Europe. And this was in 1200 AD when he wrote the Liber Abaci. So it's kind of amazing to me that the in the West, the even in ancient Greece and ancient Rome, they didn't have the concept of 0. And this was a big impediment to math. It was actually made. It turned out to be the reason why they couldn't invent calculus. You needed 0 and you needed infinity, and you needed limits. But without 0, you couldn't get limits. So it was really a problem they didn't have 0. Also, the counting system was very cumbersome without 0. I'll get into that later in the future, probably in my next video. But that's the whole numbers 1, 2, 3, 4, 5, so on. I'm calling that W just because there isn't a standard definition. Usually people write N for the natural numbers. I'm not doing that here because some people write N starting with 0 and some people write it starting with 1. So I'm just writing it. Actually, I'm writing it as N. Yeah. N is the natural numbers. That starts with 1. W, I'm writing W for the whole numbers. Whole numbers do start with 0. Nowadays, people usually call this set N, but in the old days, they called it the whole numbers. So the only difference between N and W is that W has 0 in addition to 1, 2, 3, and so on. So it just has one more element. And then the next set out is the integers. So the next of it, once you have 0 and the positive numbers, it's kind of natural to go to negative numbers too. Negative integers, -1, -2, -3. I'm sure you guys all saw the number line when you were in grade school. So these are just the integers. You kind of reflect them about 0, and then you get positive as well as negative integers. And then after that, you get the rational numbers. You get fractions. So it turns out you can get more numbers if you divide integers by other integers. In general, that doesn't give you an integer anymore, like 1/2, 3/4, 4/5, 7/5. Doesn't have to be a proper fraction. Numerator can be bigger than the denominator. It can also be negative, like -5/3, -10/7, so on. You get the idea. Those are all the natural or the rational numbers. So rational numbers are just all the fractions of integers. And for a long time, I think the Greeks thought that the rational numbers was it. They couldn't imagine what are called irrational numbers. But it turns out that there's what are called the real numbers, and this is a bigger set than the rational numbers. This one includes what are called irrational numbers, and it turns out that most square roots are irrational, like square root of 2, square root of 3, square root of 5. As a matter of fact, the square root of any number that's not a perfect square turns out to be a irrational number. And it's actually pretty easy to prove that they're irrational. And I'm going to give a proof of that when I talk about them. But after the irrational numbers, or after the real numbers was just the rational and irrational, then you get what are called the complex numbers. So the complex numbers includes things of the form a plus bi, where now I is kind of a weird number. was the square root of -1. And you might think that that number doesn't exist because all squares, at least squares of real numbers, are all non-negative. You can't square a real number and get a negative number, but you can invent a number which we call I, just the imaginary unit or the imaginary number, whose square is -1. And it turns out that this gives you a much bigger set of numbers, and it's actually a very useful set, even though it's a little bit of a strange set. So anyway, that's kind of an overview of the numbers we're going to be talking about. I talk about in my book. There are other bigger number systems in this even. There are also things like quaternions, octonions, sidonians. It turns out that you can keep extending the dimension of real numbers by powers of 2, and you can do that infinitely many times if you want. But each time you do it, you lose properties. For instance, the real numbers are ordered. The complex numbers, which includes imaginary numbers, is not ordered, but it's two-dimensional. And then the quaternions are not commutative, and the octonions aren't even associative. So they get weirder and weirder. But you can do it infinitely many times if you want. There's also some other types of numbers too. There's numbers called surreal numbers. These are kind of weird numbers. I think it was Donald Knuth who invented surreal numbers. And they're kind of fun, but they're weird. And I don't talk about them in my book. So anyway, that completes my video for today. That's an overview of numbers and number systems. And thank you for watching. Long live math, and I'll see you guys next time. Bye.